Swayam Prabha. Digital India. Educated India.
Alright, so let's begin. Let's continue where we left off in the previous class. We were discussing this problem where we had an ellipse in 2 dimensions. So this is a problem in R2. Let the horizontal axis be denoted by x, the vertical axis is denoted by y, and so we were looking at points that were lying on the surface of this ellipse. Okay, that is the black trajectory that is shown here. Okay, and a point like x star y star which lies on the surface of the ellipse, and we wanted to find a rectangle with whose endpoints are whose corner points are on the ellipse that has the maximum area. And for simplicity, we said let us take the rectangle to be aligned with the coordinate axis. So, the axis of the rectangle are aligned with the coordinate axis. Okay, so, the mathematical problem we posed was we have f0 of x comma y, which was the area of a rectangle whose corner point here is say x comma y. That you can see can be given by 4xy, and x comma y should lie on this ellipse. That means, x comma y should satisfy the equation f1 of x comma y equals alpha. That is this equation. So, f1 of x comma y equals alpha, where f1 is the ellipse equation. So, x square by a square plus y square by b square. Okay. So, any x comma y that lies on the ellipse basically satisfies x square by a square plus y square by b square equals alpha. All right. So, over all such points that satisfy this equation, we wanted to find the x comma y that maximizes the area. So, our objective was to maximize f0 of x comma y over x comma y such that, or subject to the requirement that f1 of x comma y equals alpha. And now, assuming x star y star is a local maximum. So, if x star y star is a local maximum, we said that then it is necessary that this equation holds. The equation here says f0 x evaluated at x star y star minus f0 y evaluated at x star y star times f1 y evaluated at x star y star inverse. So, this is divided by f1 y of x star y star times f1 x of x star y star. This must be equal to 0. Now, the assumption, and we said we will make the assumption here that x star that y star is not equal to 0. So, consequently, f1 y of x star y star was not 0. It is okay. It is legal to divide by f1 y of x star y star. Right. So, this so we derived we ended the class at this step, that where we derived this condition. So, now this condition can be interpreted in another way. So, let me take off from here and introduce for you. Okay, before we do that, actually let us evaluate also what the solution turns out to be. So, this it will turn out, if you solve this equation, now you get that x star y star is a local maximum, then this must hold. You can solve this equation, you get that x star y star, the values are something like this. So, you get 2 solutions, one of them is alpha by 2 square root of alpha by 2. So, you get 2 solutions, one is square root of alpha by 2 comma times a comma b, the other is negative of square root of alpha by 2 times a comma b. Okay, so, these are the 2 solutions that you get. and for both of them the area is actually the same. The area, the optimal area, let us call that m of alpha, which is the optimal value, that turns out to be equal to 2 alpha a b. So, now you get these two solutions. The reason for that, but you can check that both of them are local maxima. Essentially, what they are corresponding to are a point x star y star here and its reflection on this side, this other point here, which is negative x star comma negative y star. Okay, they are both giving you. They can both either of them can be taken as the solution. Okay. So, now let us write this condition, this red equation here in a slightly different way. Let us introduce this notation. Let lambda star be denote this quantity, which is f0 y of x star y star f1 y of x star y star inverse. Let lambda star be denote this. Then in that case, I can write this the red equation in the following form. I can simply say that f0 x. So, I will drop the x star y star for simplicity. f0 x is equal to lambda star times f1 x, and this same equation that I have written here, the blue equation that I have written here, this same equation I can just I can take f1 y of x star y star inverse to the other side and write that in this form. I get that will give me f0 y equals lambda star of f1 y. In other words, what we have, we can put these two together and write it like this. If I take the gradient of f0, then that is at x star y star at x star comma y star, that is equal to the gradient of f1 at x star y star times lambda star. So, the earlier red equation, which is kind of complicated looking, can be simplified in this sort of form if we introduce this other notation, other quantity lambda star. Now, lambda star has an important, you can see what this thing is doing. It is basically giving you an equation, it is giving you a condition that says that the gradient of the objective evaluated at x star y star is actually just a scalar multiple lambda star of the gradient of the constraint evaluated at x star y star. Okay. So, in particular, the gradients are actually collinear. One is just a scalar multiple of the other. All right. So, this condition is what we will generalize now. The lambda star here has a name. It is called a Lagrange multiplier. So, what we can do is we can the way we, instead of writing a complicated equation like the earlier red one, what we will do is we will introduce this additional variable called the Lagrange multiplier and write another equation that is in terms of x star y star and the Lagrange multiplier. All right. So, that is what we will do now. Okay. But before I get to doing this in more generality, I want you to carefully understand what exactly we accomplished when we solved this particular problem in this way. Okay. So, and then that will also give you motivation for why we should be considering the Lagrange multipliers and so on. So, how did we go about solving this problem? We said we have a way of solving we have a condition which says that, which is a necessary condition to get to a solution for point to be a solution of an optimization problem over an open set. So, when you are maximizing or minimizing a function over an open set, we know how to address that problem. We said we took this particular problem which was not over an open set, and we said let's address this in some way. So, what did we do? What were the steps we followed? So, the steps we followed was, the first step was we eliminated the y variable, right. So, we eliminated one of these variables, and this was why were we able to do this? We were able to do this thanks to the implicit function theorem. So, we will eliminate this, we eliminated this y thanks to the implicit function theorem. That then gave us as an optimization over x. So, this gave us an optimization over x on an open set. Now, when we applied the implicit function theorem, remember what did we use? We used that around this point x star y star here, we were always on the surface of this particular ellipse, right. So, could we have applied the implicit function theorem if we did not have this particular feasible region, but rather a feasible region that looked like this? You have the ellipse and also the shell of the ellipse and also the interior. Now, if you have a problem like this, where you have both the shell and the interior, right, it is not possible to say that you will be able to eliminate one variable in term and get it in terms of the other. You can do it provided you are constrained to be on that surface, because that surface gives you this additional equation which lets you solve for one variable in terms of the other. But if you can be both on the surface as well as inside, there is no definite equation that you can invoke, right. So, the kind of constraint for which we can do all these steps that we followed are those constraints where we are optimizing over surfaces. So, surfaces take the form h of x equal to 0, or in this case f1 of x comma y equal to 0, right. So, so this works for problems where we are optimizing over equality constraints. So, when you are optimizing a differentiable function with only equality constraints, then we are effectively optimizing over a surface, and then the equations of that define that surface let you eliminate one variable and get you in terms of the other, right. So, if you had both the surface and its interior, the shell of the watermelon as well as the pulp of it inside, all of that if you have, then you cannot invoke, you cannot do this. Okay. So, this elimination of y also requires this. We also later use that, later we again use the same thing. We also after writing everything in terms of x, we also saw that we took the derivative of the constraint with respect to x. You can go back and check and put that equal to 0. That also is because we are always on the surface, right. So, that again requires that you have only an equality constraint. Okay. So, the thing that what we have done here is basically if we can replicate all these kind of steps for general problems with equality constraints, we should be able to get a general purpose result for how to solve those sort of optimization problems. Okay. At the last step, what we got was we solved for x star y star. Some of you may be wondering what how did I get this? Well, this in this case we solved for x star y star, and we could get that, I could get that in closed form. It's not very hard, but in general you would have to do this numerically. Okay. So the point is to start all the effort in optimization is to start with a problem that's written in this sort of form and reduce it to something that looks like this, where you have now just an equation that needs to be solved, and then you have some ready machinery to get to solve that equation. Okay. So, all the effort is to see how problems that are posed in as this sort of in a decision making sort of form, where you have to maximize some goal subject to some constraints, and how do you get them down to a bunch of equations that need to be satisfied. Okay. All right. So, now so, I will just state for you the general theorem for when you have an optimization problem with equality constraints. So, let me write. So, rather than prove it, I will just give you intuition for how this relates to the previous example that we studied. Okay. So, let me just state the theorem. So, suppose let f0 f1 dot fm be continuously differentiable functions. Let x star be a local optimal solution of this problem. I am writing this in the maximization form just because of our earlier problem was in maximization form. So, f0 x is what you need to maximize over x, and you have to satisfy these subject to the requirement that all these equalities must hold. So, f I of x equals alpha I for all I from 1 to m. So, there are m different equality constraints here. Okay, f1 of x equal to alpha 1, f2 of x equal to alpha 2, etc. All of them should hold. So, we are optimizing over the common region that in which all of them are satisfied. Okay, and over that region, we are trying to find the x that maximizes f0 of x. Okay. Now, the theorem says the following. Suppose you look at these derivatives. Suppose at x star, the derivatives f I x of x star for I equal to 1 to m, not 0 to m, I equal to 1 to m. So, you are looking at the derivatives corresponding to the constraints here, okay, evaluated at x star. Suppose, so these are, can someone tell me what length vectors are these? If x is in Rn, so x belong, x like we are optimizing in Rn, what length vectors are these? F I of x, these f I x of x star, they are exactly. So, they are derivatives, right. So, they are n length vectors, all of them row vectors, okay, f I x evaluated at x star, and there are m of these row vectors. Okay. Now, so, there are n length vectors, m of them. Suppose that these derivatives, so they form the m of these vectors, suppose these derivatives are linearly independent. suppose these are linearly independent. Okay. So, the ones at x star are, so the derivatives evaluated at x star, these are linearly independent. Okay. Then there exists a vector lambda star, okay, and let us write this as a column vector. Lambda star is written as lambda 1 star dot 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 lambda m star. So, this vector is a m length vector, okay, this is a vector in R m. So, there are it's a collection, its components, it has one component for each constraint that is there in the problem. There are m constraints in the problem, so there is one component for each constraint. So, lambda star is in R m such that we have this. So, I look at f0x evaluated at x star, that means the derivative of the objective evaluated at x star, that can be written as lambda 1 star times f1x evaluated at x star plus lambda 2 star times f2x evaluated at x star plus dot 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 lambda m star f mx evaluated at x star. So, you can see what we have done here. We said we started with an abstract decision problem like this, which says maximize this function subject to these requirements, and what we have said is that, well, if x star is a local solution, then you must be able to satisfy these equations. What is this? How many equations are there here? So, this is one equation, but how one vector equation, right? How many components are we talking of? N of them, because these are all derivatives, right? So, they are n length vectors. So, there are effectively n scalar equations here. How many unknowns do we have? What are our unknowns? X star is an unknown which we want to find. In addition to that, the lambda is also an unknown, right? So, x star is n length. So, there are n unknowns in x star, m unknowns in lambda, because lambda is of length m, right. So, there are m plus n unknowns. You have n equations that come from here. You need some more equations. Where are they coming from? So, the other equations, there are m additional equations that we have, which comes from the fact that x star must be feasible. X star must lie in the must be feasible for the optimization problem. So, f I of x star should be equal to alpha I for all I. So, that gives you additionally m equations. Okay. So, all of these put together help you solve the optimization problem. So, you have these equations and you have these equations. So, there is this n plus m equations in n plus m unknowns. So, what we have done is basically then taken a problem like this and taken a problem, this kind of abstract problem, and said that this is it is necessary that x star satisfies a bunch of equations, but they need to be written in terms of additional variables, not just x star alone, because now constraints are involved. You need to introduce a few additional variables, and you need exactly one additional variable per constraint. Yes, yes. So, the question here is, what if the number of constraints are very large? So, what if m is very large? So, I will discuss this matter. See, if m is very large, then you are on several surfaces at once. In fact, eventually the very fact that you have to satisfy m of these equations, that itself can end up constraining x so much that you will probably even get just one solution, right. If m becomes n, for example, that itself determines which point you are on, what your feasible region is, right. So, that can happen. But usually then that is a case of a poorly formulated problem, because you have constrained it so much that now there is nothing to search really, because the constraints, there is only one alternative for you effectively. Okay. So that sort of problem can occur, but it is not a very interesting interesting thing to study, because it is probably not well formulated to begin with. Okay. Okay. Let me so again these here are the lambdas here are again called the lambda stars. These are called Lagrange multipliers. Now, while we are at this, let's also just think understand a bit about the role of all these assumptions here, for that you see how this is backward compatible with what we have seen so far in that example. Right. So, here the key assumption I have made here is that, of course, these are all continuously differentiable. That is one assumption, that all these the objective constraints, etc., these functions are continuously differentiable. And then I said that if I look at the derivatives of the constraints, they are linearly independent. The derivatives of the constraints are all linearly independent. Now, that is akin to our previous assumption here, that we had assumed that y star was, remember, y star was assumed as non-zero, y star was taken as not 0. So, we were considering, because the reason was there, because we said we do not need to look at such points. Okay. But what y star non-zero ensured was that this f1y evaluated at x star y star is not 0. The analogous thing that we need here in this more general setup is that the constraint derivatives are all put together are linearly independent. Okay. Now, what that ensures is, geometrically, what that ensures is, when you are optimizing over all these surfaces, the intersection of all of these surfaces, if the constraint derivatives are linearly independent, then that lets you lets you define what's the in terms of the derivatives, the tangent surface to all of these surfaces. Okay. So, this will become more and more evident as you go later into the course, but basically the tangent surface gets defined, and once you have the tangent surface defined, in terms of that you can we can write out conditions like this.